Just ask them. Can we start? If somebody can respond, I don't see many students. Yes.
Hello.
Hello.
You can start now.
Okay.
Hello.
Hello. Can you hear me?
Yeah.
Okay. So we'll start. So the today's topic basically continuation of the last lecture, which was the kinematics, and today we will be talking about spatial robots. So the title is forward kinematics of spatial robots. Again, I have been able to upload today's lecture material as well, and this is 12lec.pdf in my website under Ethiopia folder. Just to have a look of what we have done in the last class, I have defined kinematics. So kinematics was defined. Then under kinematics we had forward kinematics and the inverse kinematics. Just to repeat what forward kinematics means, suppose if I have this hand, if I have this hand and if I apply some joint motion here, my first joint, if I apply some joint motion here in the second joint, and if I calculate where is my end effector here, so that is my forward kinematics. In the inverse kinematics, if I give this point here, I want to calculate that how much I have to provide here and here to move there, that is inverse. We will discuss inverse later. Coming back to the project. So, we have done examples, we have done three planar examples. We have done revolute two link planar arm. We have done revolute prismatic planar arm. We have also done revolute three revolutes planar arm. Then we went ahead of the plane by considering a SCARA robot which had one vertical prismatic joint. So, if you have quick questions, I will stop here for few seconds, maybe 30 seconds. If you have questions, you can raise it now. Any questions or doubts from the last class? Okay, so yeah, okay. If you wanted to just say no, then I proceed. Okay, so as you said, I am teaching very well, everything is so clear. So I continue with today's outline. So forward kinematics for 3 degree of freedom articulated arm. So when I say 3 degree of freedom, this is a spatial arm, and typically this kind of arm, whether it is a 3 degree of freedom articulated arm or it is spherical wrist. So typically this arm's job would be to place an object to another positions. So this arm basically controls the position of a point on a rigid body. This wrist is used for orienting a rigid body. So in a way, if you look, when we go through this solution of this 3 degree of freedom articulated arm and 3 degree of freedom spherical wrist, these two can combinedly make a complete spatial robots, and that is 6 degree of freedom Puma robot. and a variation of the Puma robot is 6 degree of freedom Stanford arm. Only difference here would be that one of the joints would be prismatic, whereas in Puma robot you will have everything as revolute. Let us go. Just to remind you, forward kinematics solutions can be obtained by multiplying T1, T2 up to Tn. Since today we will be talking about 3 degree of freedom robots, arm and the wrist. So, we will have T1, T2 and T3. So far in my calculations in the previous class, I have told you that there is an alternative methods, but here I am not doing it for the alternative method, because handling 4 by 4 and just simple multiplication gives you a better understanding. So, we will follow 4 by 4. Whenever necessary, we may use the 3 by 3 equation and the vector equation. Let us move to the example now. So, this is the 3 degree of freedom articulated arm. As I told you, one of my earlier lectures towards the beginning of this course, articulated means jointed. And if you look at this picture carefully, I have a vertical axis. I have a vertical axis which is, let me try to do this pointer. So, I have a vertical axis here which is Z1, then I have a perpendicular to this vertical axis which is Z2, and parallel to Z2 I have Z3, and this is very similar to our human hand. Now, you look at my hand. So, look at my body here. So, this waist motion, this waist motion is that vertical axis. Okay. So, about this I am rotating, and then I have a elbow motion. This is my elbow motion, right. So, if this is my vertical axis here, and then perpendicular to the vertical axis is my elbow motion, and this elbow motion this is a shoulder motion, this is a shoulder motion, and then parallel to this axis, which is this axis here, I have another axis parallel here, and I have a elbow motion. So, in a way, if you look at my body now, so this is my waist motion, that is the vertical axis, then this is my shoulder motion, and this is my elbow motion. So, what you see actually on the screen, you are not able to see my the fist or the fingers. So, these 3 axes consisting that robot arm is able to place a point anywhere in the 3 dimensional, because I need x, y, z. Okay. Later on in the next example, we will see the wrist, but for the time being concentrate on the arm portion. So, an articulated arm is very similar to our human hand. Then looking at the spherical wrist, okay. Notice here what I have done is the last one for the articulated arm, this revolute joint which was parallel to this axis. So, the last one. So, for the articulated arm I had the axis like this, but for the wrist this is the axis. Okay. So, notice here the vertical axis, the perpendicular axis, and the third perpendicular axis. So, all of them are intersecting here, which I have denoted as O1, O2, O3. This is called the wrist, as you will see in my wrist now. So, concentrate on my this arm. So, I have a vertical axis. So, this is my vertical axis, that means this one is my vertical axis, right. So, this one. then I have this one, okay. So, which is about this axis perpendicular to the vertical axis, right, and then I have this one, okay. So, if you keep it in this position, the first axis, okay, and the third axis is parallel, okay. At this position there are problems, but in general this is my one axis, okay, then this is my another axis here, and then if I keep it, this is my another axis. So, vertical axis, perpendicular horizontal axis, and the third perpendicular horizontal axis, okay. So, that is the wrist. So, you have seen the arm here. So, this is the arm 1, 2, 3, and then I am adding 4, 5 and 6. So, now my hand has total 6 degrees of freedom, which will be able to move any object from one place to another place comfortably as per your requirement. And that is the reason in industry we use hand like robot for any purpose. So, let us look at the Puma robot, which we have seen towards the early part of our lectures. So, that was the Puma robot, which looks exactly like our arm. So, this is the waist one, this is the shoulder one, okay. This is the elbow, and there I have 3, and I have given the analogy with the hand here. When we solve forward kinematics, we have to represent this robot in terms of the joint axis perpendicular to the joint axis, which we will see when I do the exercise. So, then the stand forward arm, this is basically the architecture. Immediately you may not understand very clearly, but after I solve the Puma, then you will be able to understand. So, we will come back to this figure later on during our exercise. So, 4 things we want to do: articulated arm, spherical wrist, Puma and stand forward. And for your information, Puma is nothing but a combination of articulated arm and spherical wrist. So, this is my DH tables. I would like you to note it down, because now I will just take you to the figure, and from the figure we will find out what are the DH parameters. So, as I am writing down from the screen, you please write it down. I will not shift the screen for next 30 seconds. So, BI will have 0, 0, 0, theta I, theta 1, theta 2, theta 3, AI 0, A2, A3, and then you have alpha I minus pi by 2, 0, 0. So, I have noted it down for myself. BI are 0, 0, 0, theta I is theta 1, theta 2, theta 3, joint variables. AI, oops, sorry, we have to go to articulated arm. So, BI 0, 0, 0, theta I, theta 1, theta 2, theta 3, AI 0, A2, A3, alpha I minus pi by 2, 0, 0. Now, I will take you to the figure. So, now as I told you that to find out the DH parameters, first we need to concentrate on fixing the coordinate frames. So, the first joint axis is here, which is a revolute joint. So, I have put a Z1 here. Okay. So, let me highlight. you have Z1 here. Okay. So, that is my first axis. Then you have the second axis for which this is your Z2. Then the third axis Z3. Again, please remember, I could have 1 minute. Okay, let me take this pointer. So, this is Z1, this is Z2 and this is Z3. Please note that I could have done Z3 in these directions also, there is no harm. I just took it Z3 parallel to Z2. Now, if you remember the definition of DH coordinate frames, the common perpendicular to Z1 and Z2 is x2. So, now I have put common perpendicular to Z1 and Z2 is x2 here. Then common perpendicular to Z2 and Z3 is x3 here. Okay. So, I have set it up. Now, the two arbitrary one are the 1 and the last one. So, one may think to put x1 here, but if you think carefully, putting x1 here and here does not make any difference as far as the motion is concerned. Okay. So, if I put it in the previous location, there will be a distance coming into picture, this distance. So, I just wanted to make this distance 0. So, I put it parallel to x2 here. Okay. And then the x4 I made it parallel to x3 and z4 I have parallel to z3. So, now my setting is complete. Now, you refer to the values which you have noted down. Bi, that means B1. So, B1 is the perpendicular distance from Z1 to Z2. So, do we see any distance between Z1 to Z2? Here the Z1 and Z2 intersecting. So, they are not intersecting at any positive or negative value. So, they are 0. So, B1, the table you have noted down, comes out to be 0. Theta 1 is the joint angle between x1 and x2. So, this is my x1 here. So, this is my x1 here and this is my x2 here. The way the drawing is made, they are at the same location. So, at this position theta 1 is 0, but notice that this joint will move. So, which means what? Which means this will come after some time at this position, right. So, at some position like this. So, obviously, then you will have some value theta 1, which is a joint variable. I will give input to control this robot. So, this is theta 1 is a joint variable. So, if you look at your table, we put it theta 1 as a variable. Now, A1 is the distance between Z1 and Z2. So, again coming back, so there is no distance here, they are intersecting. So, A1 is 0. Alpha 1 is the angle between Z1 and Z2 and measured positively about x2. So, now Z1 to Z2 is this angle and this is not. So, this is positive about this axis, which is negative of x2. So, alpha 1 will come out to be minus 90 degree or minus pi by 2, as I have noted you down in the table. So, we have done for the first pair of joints. Now, move to the second pair of frames. So, B2. So, B2 is the offset between x2 and x3. So, this is my x2 here and this is also x3 here. So, there is no offset. So, B 2 is 0. Now, theta 2 and theta 3, sorry, theta 2 is the angle between x 2 and x 3. Note that this x 3 will sometime will move to these directions. So, then this angle would mean theta 2. So, that is a joint variable kept as theta 2. The distance between Z 2 and Z 3. So, this is your distance between Z 2 and Z 3, that is given as A 2. So, in the table you see you have A 2, and the last one is the angle between Z 2 and Z 3. Since Z 2 and Z 3 are parallel, so obviously they have angle 0. So, alpha 2 is 0. Coming back to the last set of parameters, that means the relation between this frame 3 and frame 4. Again, the distance between x 3 and x 4. So, they are in the same line here. So, B 3 is 0. Now, theta 3. Okay, I made a mistake here. This is theta 3 here, this is theta 3 here, and this is the horizontal motion happening about this axis. So, that was theta 1, but there would be vertical motions also about this. So, then this from the plane, this will be theta 2, this is the theta 2. Okay. So, please correct it. So, there is a theta 3 here, and then distance between Z 3 and Z 4, which is this distance, which is A 3, and angle between Z 3 and Z 4, since they are parallel. So, they are 0. So, this way we complete the DH parameter of this articulated arm. If you have quick questions, I can wait for about 15 seconds before I show you the transformation matrices and the forward kinematics result. If there is a doubt, please ask me. Okay. So, I hope you have noted down that table, because now we have to form the transformation matrices. Okay. So, we go back. Okay. Now, this is the value which you have already noted it down. So, we move forward now to form the transformation matrices. Now, transformation matrices we have done in chapter 5. Chapter 5, let us I think it was, I have shown you in the 10th class, not 10th class, 9th class. So, we have in the, so we have done we have okay, next one, yeah. So, this one is our the transformation matrices. So, if you take this expression, you can note it down, because we will form T1, T2, T3 to see if they are rightly done. Since I have written down the table left to me, I am doing it from there. Since theta 1 is a variable quantity, so this remains as a cos theta 1 and sin theta 1 0 0. So, you can write it down, we will check from the expression later on. Alpha 1 is minus pi by 2. So, cos pi by 2 is 0. So, these two term then becomes 0 here, and sin alpha 1 will become minus 1. So, this column will be 0 0 minus 1. So, this will be minus sin theta 1 plus cos theta 1 and 0. Okay. So, let me write it down parallelly what I am telling you. So, cos theta 1, sin theta 1, 0, 0. So, this is my T1, then 0, 0, 1, 0, this is minus 1, this is minus sin theta 1, cos theta 1, 0, 0, and then I have a cos theta 1, so a1, so a1 is 0, so this will be 0, 0, and b1 is 0, 1. So, I have just noted down the T1. Now, I will show you the expression of T1 from today's lecture. So, you see this is my T1 here, cos theta 1, sin theta 1, 0, 0, 0, 0, minus 1, 0, minus sin theta 1, cos theta 1, 0, 0, then 0, 0, 0, 1. Okay. Now, if you try for the second set of DH parameters in the second row, we can find that this will be cos theta 2, sin theta 2, 0, 0, minus sin theta 2, cos theta 2, 0, 0, then 0, 0, 0, 1, 0. Since A2 is non-zero, so it will be A2 cos theta 2, A2 sin theta 2, 0 and 1. And then we have just okay. Then similarly for T3 you can have it. Now, let us do the multiplication of T1 T2, and then the resultant of T1 T2 with T3 I will leave it to you, but let us try to do this T1 T2 on the paper here. So, I have T1 here, T2 here. So, I write cos 1 sin 1 0 0 0 0 minus 1 0 minus sin 1 cos 1 0 0 0 0 0 1, and then for T2 it will be cos 2 sin 2 0 0 minus sin 2 cos 2 0 0 0 0 1 0 A2 cos 2 A2 sin 2 0 1. So, let us do this operation. So, this is your T1, this is your T2. Okay. So, we do the multiplication, cos 1 cos 2 0 0 0. Okay. So, this is cos 1 cos 2, then sin 1. Please note that I always want to calculate the columns first. Sin 1 cos 2 0 into sin 2 0, cos 1 into 0 0, 0 into 0 0. The third one 0 into cos 2 0, minus 1 sin 2 minus sin 2, then 0 0. Okay. The third one is 0. So, the next column cos 1 minus cos 1 sin 2, this is 0, this is 0, this is 0. Next minus sin 1 sin 2, 0 0 0. Then this will be minus cos 2 0 0. So, all zeros. Last one 0 0 minus sin 1 minus sin 1 0 0 0 cos 1 0 0 0 0 0 0. So, this will be A2 cos 1 cos 2 0 0 0, A2 sin 1 cos 2 0 0 0 0 minus A2 sin 2 0 0, and then this is 1. So, this is the multiplication of T1 and T2. This result needs to be post multiplied by the result of the third frame, which is on the screen, T3 here, and then the final result I am showing it. So, this is the final result in the highlighted box, and this is the result. This is cos 1. So, cos 1, cos 2, 3, cos 1, cos 2, 3, sin 1, cos 2, 3, minus sin 2, 3, 0. So, this portion basically, like if I divide this matrix. So, this portion will mean the orientation of the fourth frame with respect to the first frame, and this portion will mean that this is the origin of the fourth frame from the origin of the first frame. Okay. So, I will calculate now the DH parameter of the spherical wrist. So, let us look at the spherical wrist. So, we look at the spherical wrist configuration. So, this is perpendicular now, and again like before, one of the important point in finding DH parameters and then do the forward kinematics is to appropriately place the coordinate frames, and without good practice it will remain a very difficult task and a confusing also. So, please do practice. So, here I have the first axis. So, I have the first axis here. So, I have the first axis like my previous arm, then this is the second, and this is my first axis, this is my second axis, and this is my third axis. So, I put my first joint axis Z1, the second joint axis Z2, and the third joint axis Z3. The perpendicular between Z1 and Z2 is x2. So, I have defined here is x2. The common perpendicular between Z2 and Z3, which is sitting here, should be x3. So, common perpendicular x3 is sitting here. Okay. And now, the frame which should be attached to the end effector is Z4 here and x4 here, and for your information, the origin of the frame which is connected to this end effector is also sitting here. This requires little imagination. So, please try to imagine that I am telling this is connected to here, but its origin sitting here. What does it mean? In case of difficulties, we will discuss during our personal visits. So, in a way, I will get rid of this all this clumsiness, this card. So, in a way, all three coordinate frames, rather all four coordinates, the fourth one I have not written it here, are sitting here, and this is the typical of a spherical wrist. Please remember, spherical wrist will have three perpendicular axes for the revolute joints intersecting at a point, and this is true for our hand also. You look at my wrist, is the same thing. So, one axis, second axis and third axis, and this is intersecting at this point, and this is helpful when we do the inverse. Remember, inverse problem we have not started doing yet. When you do the inverse kinematics of the total 6 degree of freedom, this kind of property will help us to simplify the problem. we will discuss when you go then. So, now if you write the DH parameters for this spherical wrist, one can write beta b 0, theta 1 joint variable, a 1 0 and alpha 1 pi by 2. Just for your convenience, I will do the first set, leaving the other sets as it is. So, b was the distance between x 1 and x 2. So, there is no distance here, this is 0. Theta is the angle between x 1 and x 2, as I told you like in the previous case. So, as the first joint will move, okay, this x 2 will probably will come here. So, this will become the new x 2 position. Okay. So, then this will become a theta 1. So, it is a joint variable. So, theta 1 is a joint variable. Then we have a is the distance between x 1 and x 2, sorry, z 1 and z 2. So, again z 1 is here, z 2 is here, no distance 0, and angle between z 1 and z 2 about x 2. So, this is a 90 degree here. So, that is pi by 2. So, we go back. So, that is the thing we see it here 0 theta 1 0 pi by 2. If you do similarly for the other 2 0 theta 2 0 minus pi by 2 0 theta 3 0 0. Okay. So, it will be done, and now if you put that expression of homogeneous transformation T in terms of thetas and alphas, you will be able to get the expressions for the homogeneous transformations as this T 1 and T 2 and then T 3, and if you multiply them you get the T, you will get this T as a complete 1, where if I again partition it here, so these portions, this portion will be your orientation matrix of coordinate frame 4, and these portions will mean that it is the position vector of O4 from O1. As we have seen the way we have put the coordinate frames, the origin of the fourth coordinate frame is located at the origin of the first coordinate frame. I will show you. So, origin of the first coordinate frame. So, you see origin of the fourth coordinate frame, I told you it is sitting here. So, it has a coordinate 0 0 0, and that is been reflected in the here. So, now we need to do the thing for Puma robot. Puma robot I have showed you. If you want to see again, I will show you again. So, this is our Puma robot, and now I will show you after putting its coordinate frames. I will switch between two figures 2-3 times, so that you are able to correlate. So, the first one, you see this is my waist motion, okay. First revolute joint, and I have the revolute joint axis Z1. Then I have, this is Z1, then I have my shoulder motion, and for which I have this joint axis Z2. Next, parallel to the shoulder, I have a elbow motion, which is shown as axis Z3. With this, I am attaching the wrist. So, up to this much, this is like my articulated arm. With it, I am now connecting my wrist joint, which is, this is my Z4, and Z4 is here, and then I have a perpendicular to it Z5 which is here, and then this is my Z6 as per the symbol we have adopted, and this is my X6, and notice all of them are intersecting at this point. So, the way we have analyzed the spherical list, all the coordinate frames of last 3 joints origins are taken at that big red dot points. Okay. Now, after that I have applied the DH formulas to set other axes. So, common perpendicular of Z1 and Z2 should be my x2. So, I have drawn x2 here as a common perpendicular. Common perpendicular of Z2 here and Z3 here should be your x3, and if you notice here, so this should be your 1 minute, this is x2, sorry, this is Z2 here and Z3 here. Okay. So, actually it is put in the vertical line. So, this is the x3. So, this is a little vertically up. So, this is the x3. So, so and so forth. It requires very patient drawing of the axis. It may take some time before you are overcoming the confusions. Anyway, so this would be your kind of a homework to see, because in the small screen it may be very difficult to show you all the lines. You can draw yourself and try it. So, once you have done it for the arm and wrist, this will not take a very long time to understand what is happening. So, these are my DH parameters listed in this table. What I have put it here 0, minus pi by 2, 0, 0, 0, it means they are the angles corresponding to the diagram I have just shown, because in the diagram we have to show a particular configuration of theta. So, at this point theta 1 is 0 and theta 2 is minus pi by 2, which means what? Theta 1 0 means x 1 and x 2 axes are at the same line. So, x 1 and x 2 are at the same lines here. Theta 2 minus pi by 2 means x 2 and x 3 are at 90 degree negative of z 2. So, this is your x 2 here. So, this is your x 2 here and this is your x 3 here. Okay. So, about z 2 they are causing a negative of pi by 2. So, from this is parallel to x 2, and from x 2 to we are going to x 3, and which is negative of this. So, minus pi by 2. So, those in the square brackets I am putting the values corresponding to this diagram. Now, if you want to find out the expressions like I have done it in the previous cases here, which is in terms of variable theta 1, theta 2, theta 3, one can also get an expression in terms of theta 1, theta 2, theta 3, but it will be relatively very complex expressions. One can do the programming and can find the results. I just tried to avoid those expressions in the book as well as in this lecture. What I wanted to verify is, if theta 1, theta 2, theta 3 has these numerical values which I have displayed here, then what will my calculation become? So, based on this theta 1 as a particular values of 0 and etcetera, if you calculate the orientation matrix Q and the position vector of the origin of the 7th frame, because this has 6 degrees of freedom. So, the 7th frame will have these values. Let us try to understand little bit of physically, because only mathematics is not good. We must be able to correlate with the physics of the mathematics. So, the Q which I have calculated, which you can try yourself also by hand. I repeat, if you want to calculate in terms of theta 1, theta 2, theta 3, it will give you very complex expressions. What you should do is, you should put the value of theta 1 as 0, calculate T 1, put the values of theta 2 as minus pi by 2, calculate T 2, similarly T 3, T 4, T 5 and T 6. And then if you multiply those one, you will get Q portion as an identity matrix, which means the 7th coordinate frame is parallel to the first coordinate frame. Is it true? Let us look at the diagram. So, the 7th coordinate frame, in this case I have indicated as an end effector coordinate frame. So, x e stands for 7th coordinate frame or end effector coordinate frame, z e is the end effector coordinate frame z. So, x e is parallel to x 1 here. So, that is why it has 1 0 0. Z e is parallel to z 1. So, that is the reason it has 0 0 1, and obviously, if x 1 and z 1 parallel to x e and z e, y 1 should be parallel to y e, and you get this identity matrix. Okay. If your calculation does not show it as an identity matrix, but from the physics or the geometry of the manipulator, you see they are appearing to be parallel. So, you have made some mistakes somewhere. That is one way to debug your results. For P stands for the origin of the end effector from the coordinate frame A 3, B 2. Let us remember first two. So, which means okay, I will show you. So, which means this distance, which means x 1, x 2 is here, which means we are talking about this distance. So, the coordinate, so this vector, okay, so this vector should be our p vector. So, this is our p vector. So, if you notice along x 1, it will have a value A 2, and then 1 minute. Let us go back. So, this will have a value A 3. So, x component of the end effector, the A 3 B 2. So, this along this, so this will have A 3. So, A 3 is this distance here, A 3, okay, and then it will have, oh, I am sorry, P is not that one, P is this one, P is this one, I am sorry, because the origin is lying here, okay. So, this is your P. So, this one will have a distance A 3 here, and then there will be B 2. So, what is B 2? So, this is your B 2 here, okay, and so on and so forth. So, please check, and if there are any confusion, I will clarify when I am there. Okay. So, now we go for the Stanford arm. What we do in the Stanford arm, this is a research robot of Stanford University and USA. So, it is become very popular as a Stanford arm. In Stanford arm, we replace we replace this joint. In Stanford arm, we replace this arm using a prismatic arm. Okay. So, I will show you now. So, now let us look at this thing. So, the first joint is a revolute one, the second one is also a revolute one, the third one is a prismatic one. When prismatic joints come, you may apparently find it little confusing. For that, you should always go back to your RP example or maybe PR example, get your doubts settled before you come for 6 degree of freedom robot like this one. Then again the fourth, fifth and the sixth one are same as the previous one, they are basically spherical wrist. For this robot, I again wrote the TH parameter variable. Theta 1 is the revolute one, 0 corresponds to the positions of the diagram. Theta 2, B3 is the prismatic joint. So, it is the joint variable here, and then theta 4, theta 5, theta 6 and so on and so forth. Again using the values of those joint variables corresponding to the diagram, if I calculate Q, it shows this matrix where the first column is -1 0 0. If we compare with our direction cosine representation of a rotation matrix, this means the end effector coordinate frame is the x axis of the end effector coordinate frame is the negative of x 1. Let us see if that is correct or not. So, this is my end effector coordinate frame x 1 here. So, this is my x e, the end effector coordinate frame axis x, which is negative of, this is my positive x 1. So, this is the negative x e minus 1 0 0. What about z e? Z is along these directions, z 1 along this direction. So, it should have the same 0 0 1 and y. So, this is my y 1 and here y should be in which directions? Y should be in this direction, y e. So, y e is negative of y 1. So, y the second column should come out to be 0 minus 1 0. So, second column should come out to be 0 minus 1 0 and the z is parallel to the z 1. So, 0 0 1, it is correct. If you can visualize the geometry of the origin of the last frame, that means my P would be this one. So, the P is this should be the P vector, and you can try to understand from this geometry what should be the value of P, and you can check that this should be coming out to be this value. Okay. So, with this I want to end the forward kinematics and would like to introduce the concept of inverse kinematics with respect to the 2R planar arm. But again, before I switch to inverse dynamics of planar arm using the papers, I would wait for about a minute in case you have some questions. Any questions about forward kinematics? Seems no question. Okay. Let us move to the basics of inverse kinematics. I wanted to show this figure again, what I showed yesterday. So far what we have done, that we have learned how to do this one. This is another terminology, direct kinematics. So, forward kinematics or direct kinematics, which means you provide these values, theta values. I will tell you what is q and what is p. Okay. But now we will start with inverse kinematics, and I wanted to show you this diagram corresponding to a 3 degree of freedom planar robot arm. You see this P point can be reached by the solid line here, okay, which is shown here, or it can be reached through this dotted line here. So, this is the one which makes our task very, very complex. Okay. Whereas, for the forward kinematics, so for all the examples we have seen, starting from planar 2 degree of freedom robot to spatial 6 degree of freedom robot, all the cases we have found out only one solutions, or we call it unique solutions. Okay. Now, let us see if I have this robot, how would we proceed? I will go to the paper. So, this is the arm, and this is as per DH notations. This is my x1, this is my y1, this is my x2, this is my y2. Just to remind for our convention, x2, y2 is attached to link 1. I kind of welded it. Then here will be my x3, y3, okay, and again this is kind of welded here, and this angle is theta 2. If I redraw it, indicate my other important variables, means this is my px, py, which means this value is px, this value is py. Now, for this case, T matrix has come out to be, here you had cos 1 2 sin 1 2 0 0 minus sin 1 2 cos 1 2 0 0 0 1 0, you had a 1 cos 1 plus a 2 cos 1 2, a 1 sin 1 plus a 2 sin 1 2. I remember this. you can check. This is a 2 degree of freedom. This is a 2 degree of freedom. Okay. Using a 2 degree of freedom robot, I can at the most control 2 parameters, and in this case I want to control 2 parameters which are p x and p y. That means I will move it in certain new positions like this and certain new positions like this. That means I bring point A to point B. So, that is the way the task of this robot would be, and these portions q I will not be able to control it. Whatever control I do for p x and p y, something automatically will obtain as a q. So, I do not have any control over q. I have a control over this p x and this p y. Whatever I control do p x and p y, and correspondingly whatever q becomes, I have to happy with it. If I want to control q also with this robot, it cannot be done. Okay. Okay, so, let us be happy with controlling 2 parameters. So, this corresponds to this vector, right, p. So, this is a p vector whose components are p x, p y. So, let me write p x is equal to a 1 cos 1, a 2 cos 1 2, p y is equal to a 1 sin 1 plus a 2 sin 1. By the way, do not forget what is my task. For the forward kinematics problem, our task was I give all these parameters and I calculate this one. Now, I provide you this and I ask this, and this question means I ask what is theta 1 and theta 2, and here this, and I give t means I basically provide this one, because it is a 2 degree of freedom robot. It can control only the positions p x and p y. So, this I will provide and I will calculate theta 1 theta 2, which means here I provide this, I provide this, and I ask this and I ask this. Okay. So, given p x p y, given find theta 1 and theta 2. So, how to do it now? Okay. This is, so far we have done only matrix multiplications. Matrix multiplication means only multiplications and additions, and I pointed out forward kinematics is simple multiplication addition. Now, we have 2 equations. So, I have 2 equations and I have 2 unknowns. Of course, as per mathematical knowledge, we know I am able to solve it, but these 2 equations and 2 unknowns, these 2 unknowns are in terms of sine and cosine as it appears here. So, this means this is non-linear. So, non-linear equations. So, we are making life little more complex, means we want to solve 2 nonlinear equations to obtain the values of theta 1 and theta 2, and nonlinear means depending on the degree of nonlinearity, number of solutions will be that many. We will see how many solutions it will have. I rewrite p x a 1 cos 1 plus a 2 cos 1 2, p y is a 1 sin 1 plus a 2 sin 1 2. Okay, so, now I have to extract theta 1 theta 2 from here. How do I do it? Let us square it, square it, square it. then add it. What do we get? We get px square plus py square equal to a1 cos 1 square plus a2 square cos 1 2 square plus 2a1 a2 cos 1 2 from the first equation. From the second equation, a1 sin 1 square plus a2 square a1 square a2 square sin 1 2 square plus 2a1 a2. Okay. So, I add them. So, left hand side remains as px square plus py square equal to. So, these two will become a1 square. We know sin 1 square plus cos 1 square is 1. These two similarly will become a2 square plus 2a1 a2. If you added them, cos 1 2 plus sin 1 2 is cos a minus b. So, this will be cos theta 1 plus theta 2 minus theta 1, because cos 1 2 means this is cos theta 1 plus theta 2. So, that is the thing, cos this is theta 1 2 minus theta 1. So, this cancels out. So, finally, px square plus py square minus a1 square minus a2 square divided by 2a1 a2 will become cos theta 2, or we are writing cos 2. So, we are able to express cos theta 2 in terms of my given values and known geometric parameter of the robot. So, from here I can calculate theta 2 as cos inverse whatever this value I calculate. But I will not calculate theta 2 using cos inverse. One of our mathematical fundamentals class, I have told you any angle we should find out as a tan inverse or 2 tan a2 tan function. So, from here I would rather first find sin theta 2 as square root of 1 minus cos square 2, and here I will have plus minus sin. So, once I have found out sin theta 2, so then I will use my a tan 2 function as this will be sin theta 2 and cos 2. So, I will obtain theta 2. Once I obtain theta 2, notice here to get theta 2. So, I have one corresponding to plus values, and because there is a plus and minus both, and so I have another solution a tan 2 minus sin 2m, and this will give me another solution. What do they mean? This means I can reach with these theta 2 values, I can reach with these theta 2 values. So, these two theta 2 values, theta 2 1 and theta 2 2 corresponds to this one value and the second value. Once I calculate this sin theta 2, then I can substitute back in my first equation here, okay, and I can calculate what will be my theta 1. For that, what we need is we need to expand this here. Let me try to give you some hint before I leave it to you for further calculation. So, a1 cos 1 plus A2, this was cos 1 2, this is Py was A1 sin 1 plus A2 sin 1. So, this will become Px equal to A1 cos 1 plus A2 cos 1 cos 2 minus sin 1 sin 2, and this will become Py A1 sin 1 plus A2 sin 1 cos 2 plus cos 1 sin 2. So, from there I do Px A1 plus A2 cos 2 cos 1. So, I have taken cos 1 common here and then left A2 sin 1 sin 2, and I have do Py as A1 plus A2 cos 2 sin 1 plus A2 cos 1 sin 2. So, since I have already calculated sin 2 cos 2 in my previous step, so now this is also known to me. This is also known to me. So, now only parameter is remaining here is cos 1 and sin 1. So, you can multiply this one with certain factor and this one with certain factor, and then you can add them to calculate sin 1 equal to something, cos 1 equal to something, and this I leave to you and check from the book. And since sin 2 had two values plus and minus, obviously you will have two values which will correspond to your two theta 1 values, and I turn this page and show it here. So, this is one theta 1 and this is another theta 1. So, for 2 degree of freedom robot arm, you will have two solutions. In real life, it will be a challenge for the programmer to decide which solution a robot should move. As I told you in yesterday's class, that is a separate research domain. We will not take those issues in this course. So, with this I want to kind of close today's lecture. If you have questions, you ask me, otherwise I will give you the summary of today's lecture. So, I wait about 30-45 seconds to give you the chance. No question? Okay. If you have been able to solve for 2 degree of freedom, for 3 degree of freedom planar robot, I would request you to look the diagram in the book before you come to the next class. So, let me summarize by saying that DH parameters of several spatial robots I have shown, transformation matrices are calculated and forward kinematics results, and also I have done the inverse kinematics for the 2 degree of freedom planar robot. So, with this I want to close, but still if there is a question or comments, if you want to take me specially something from here, please tell me, because I have 2 more days. If you want anything specific, Do you want me to carry the model which I have been showing you through videos, the small model of a robot? Hello?
We want the model
Okay.
and then done to bring it.
Okay, I will bring the model. Okay. Anything else specific, if you can remember, you let me know. Nothing specific? Okay. So, thank you for today, and we will continue in the next class taking the 3 degree of freedom planar robot arm.
Excuse me, Professor.
Yes.
If you have any simulation software to demonstrate for the students, probably to bring with you.
Can you be a little louder?
If you have any simulation software,
Okay.
yeah, that would be beneficial.
Okay, I will see if I can bring something. Okay. Okay. Okay, thank you. Bye bye.